Okay, so this video is meant to walk you through some examples of electric field and electrostatic force. So this first example is a charge of positive 15 millicoulombs is placed at the origin. What's the magnitude and direction of electric field at y equals 1 meter? So let's just draw this out in terms of kind of situation what it looks like. So I've got this charge. It's 15 millicoulombs, and we're told it's at the origin. And it is a positive charge. So positive charges have, let's go with green, positive charges have electric fields that are going away from them. And so it's going outwards. And our point of interest is actually y equals 1 meter. So we're trying to figure out, like, at this point right here, at y equals 1 meter, what is the numerical value of the electric field and what direction is. So we can see from our drawing that the direction of the electric field at that point is upwards, okay? In terms of the calculation for electric field, that is going to come from our model here. Electric field is equal to KQ over r squared, where q is the numerical value of the charge, r is the distance from where the charge is to where our point of interest is, like where are we asking for the electric field, and k is Coulomb's constant. So recall that Coulomb's constant is 9 times 10 to the 9. Q is the value of our charge, which is 15 millicoulombs, so 15 times 10 to the negative 3, and then divide that by that distance squared, so that's 1 meter squared. And we should be able to calculate that out. Again, this is good practice in plugging in with big numbers using the E button on your calculator. And you should get that it is 1.35 times 10 to the 8 newtons per coulomb. That is the units for electric field, and the direction is up. Or you could say north. The second part of the question says, if a 2 millicoulomb charge is placed at y equals 1 meter, what force will it experience? Ooh, there's a error there in terms of spelling. So we know that electrostatic forces are due to electric fields, and so this is the relationship, Fe equals EQ. E being the electric field of charge 1, Q being the charge of object 2. So we know the electric field. If we call this particle 1, and we were to say, okay, if I'm going to put this, let me erase that there. If I'm going to put a 2 millicoulomb charge there, this would be my charge 1, and I know the electric field at that point, and this would be my charge 2. So my electric field is this known value of 1.35 times 10 to the 8th, and my Q2 would just be 2 millicoulombs, so 2 times negative 3 coulombs, and so the electrostatic force due to that is just that product, so 2.7 times 10 to the 5th newtons, because that's the unit for forces, and the direction is just the same as the direction of the electric field, so this would be up or north. Okay, let's try this next one. This is a force of 4,400 newtons exists between a positive charge of 800 microcoulombs and a charge of 300 microcoulombs. What distance separates each charge? So this is my electrostatic force. This is my Q1. This is my Q2. What distance separates these charges? So Fe for 2-point charges. So this is the electrostatic force between a field and a charge. This is the electrostatic forces between 2-point charges, K, Q1, Q2 over R squared. So in this case, I know my force is 4,400 newtons. I know my Q, or rather my K, is 9 times 10 to the 9. Q1 is 800 micro, so times 10 to the negative 6 coulombs. Q2 is 300 micro, so 300 times 10 to the negative 6 coulombs. And then I'm trying to find my distance. So for this one, I am not going to give the answer. We can go over the answer in class, but it's a matter of algebra, and so you should be able to solve for what R is. Okay, and one last question, and this is looking at finding what the net force is. And so the net force we've done net force in the past with mechanics. In terms of electrostatics now, we just have to figure out, well, what are all the forces acting on that particular object, and then am I going to add them or subtract them? So it's going to be very similar to what we did in the past. We're going to draw the forces, draw a force diagram, etc. So it says, consider 3-point charge on the x-axis. Q1 is at the origin. and it is a positive charge. And Q2 is at x equals negative 0.36, so Q2 is here. And I'm gonna, let me do Q3, and Q3 is over here, and it's positive. So I'm just gonna do a little overlay here. This is a negative charge, this is a positive charge, and this is a positive charge. And it says to, and we have these distances here. We know that this distance, we know that this distance between Q1 and Q2, because Q1 is at the origin, the distance between Q1 and Q2 is 0.36, and the distance between Q1 and Q4 is 1.44. Okay. So if I'm thinking just about forces and drawing force diagrams, I know if Q1 is positive and Q2 is negative, then Q1 is going to be attracted to Q2. So the force on 1 due to 2 is going to push it to the left. The force on charge 1 due to charge 2 is going to push it to the left. Same kind of thought process between Q1 and Q3. Q1 is positive, Q3 is positive. So Q1 is actually going to be repelled. So the force on Q1 due to charge 3 is going to be to the left as well. Okay, so those are the directions. Now let's figure out just what innately are the magnitudes of those forces. So F12 would be KQ1 Q2 over R squared. And F13 would be K, and I'm going to call this R2 because it's the distance to charge 2. F13 would be KQ1 Q3 divided by R3 squared. Okay, so that is just kind of how you'd set it up. In terms of plugging in, K is 9 times 10 to the 9. Q1 is 4.92 times 10 to the negative 9. Q2 is 6.99 times 10 to the negative 8. Notice, I did not put the negative there, okay? It is a negative charge, but I've taken into account that it's a negative charge in my drawing here and the fact that it's going to be an attraction. You do not put the positive, negative charges in the force equation. And then the distance between those is 2.36 squared. So you should be able to calculate what that is. And then for F13, 9 times 10 to the 9. My Q1 is still 4.92 times 10 to the negative 9. My Q3 is 5.65 times 10 to the negative 9, and then divide that by R3, which is 1.44. And you should be able to calculate that. Okay. So again, this is going to be one of those where I expect you to calculate out what these values are. We're going to go over it in class. And then to figure out what the net force is on Q1, look at your diagram. F12 is to the left, F13 is to the left. And so to find the net force on F1, we would just add F12 plus F13. We would get some value, and this would be, the direction will be to the left. Okay, so do those calculations your own. When we get back to class, we will go over them.